Welcome back to ME 760 Engineering Analysis 1. So last time we were discussing the vector calculus and we talked about the divergence of scalar quantity. So now we will continue what we were discussing. So one of the application of the gradient of a field, for example, excuse me, is to be able to calculate or to figure out what is the normal to a surface. How to calculate a normal to a surface. So let's assume that we have a surface like this, and let's assume we have ionic area or something like this, and this is normal. So usually we indicate the normal by a hat on top of it. So let's assume that we have a surface, and this surface is S, so that it's a function of X, Y, and Z. And you knew from chapter number 9 that the surface will take a formula like this: f of X, Y, and Z is equal to some constant C. So let's assume that there is a curve. There is a curve on this surface, and this curve is just R of U, where U is or R of t, where t is time. Let's assume that there is a particle rolling over the surface, and this is R of t. So R of t is just equal to some x of t in the I direction plus y of t in the jth direction plus z of t in the kth direction. So because this is an R of t, which is a curve on the surface, so this means that this curve must satisfy what? The equation of the surface. So because it is on the curve, on the surface, the curve is on the surface, so it must satisfy the equation for the surface, and in this case it will be f of x, but x is what? X of t, and y of what? Y of t, and z is z of t is equal to some constant y. So if we differentiate or try to get the tangent for this curve on the surface here, the tangent is just r prime of t, and it is a vector, which is equal to x prime of t in the I direction plus y prime of t in the jth direction plus z prime of t in the kth direction. So if you try to differentiate this function here, the function f of x of t and y of t and z of t, if you try to differentiate it, so you will notice that the differentiation yields df, because it has three independent variables, x, y, and z. So it will be df by dx multiplied by what? Dx by dt plus df by dy multiplied by dy by dt plus df by dz multiplied by dz by dt, and it is equal to the left hand side, the differentiation of a constant, equal to 0. So this will be df by dx multiplied by x prime of t plus df by dy multiplied by y prime of t plus df by dz multiplied by z prime of t equal to 0. And I can write this as the gradient of the function s dotted with r prime, and this is equal to 0. What does it mean physically or geometrically? It means that you have what? You have your gradient is perpendicular to what? A tangent to the what? A tangent to the curve that lie on the surface. So if you have lots of what? Lots of curves here on the surface, all those curves, let's say, if we would be able to find the let's say the tangent to the let's say to this curve, and tangent to this curve, tangent to this curve, tangent to this curve, we will find what? A surface of what? Of tangents. So this surface of tangents will be, let's say, having an equation that represent r prime, and if you dotted the divergence of the function f with this tangent, will give you 0. This means that they are what? They are perpendicular. So this indicates that they are perpendicular. So we see that gradient of f is a vector perpendicular to a point on surface. So let's take an example. We have a sphere. And this is r, the radius of the sphere. And let's assume that this is an area here, and we want to calculate the normal to the sphere itself. So what's the equation for the sphere? X squared plus y squared plus equal to r squared, or x squared plus y squared plus z squared minus r squared is equal to what? 0. So in this case, I can calculate the gradient, and the gradient will be what? Normal to the surface. We just describe it right now here. So the gradient of f will be just to differentiate this with respect to what? So it is d by dx in the I plus d by dy in the j plus d by dz in the k direction. And in this case, you will obtain that gradient of f is a vector, and d by dx for this is what? 2x in the direction of what? I plus in the direction of y, j plus 2k 2z in the direction of k. So now, if I want to calculate a unit vector in this case, what should I do? So this will be just x in the I plus y in the j plus z in the k, and I divide by what? Magnitude of this is what? It's 4x squared plus 4y squared plus 4z squared. 4 will be outside the square root. It will be 2. 2 will cancel with 2. And you'll have x squared plus y squared plus z squared, which is what? R. So it will be just 1 over r, x in the direction of I plus y in the direction of j plus z in the direction of k. Another example for the gradient is if you have a central field. What do we mean by central field? A central field means that the force from this field is always directed to a center. Is always directed to what? A center. And usually it goes inversely with what? With the distance. So central field, the force will always be proportional, let's say, to r or r squared or whatever, and it will be in the direction of what? Of r. This is called central field. The force, like what? Gravitational field. And what is? What else? Electrostatic field is also gravitational, is also central field. And usually this force, if you study mechanics, you will notice that if you have central force field, usually the field is what? It's called what? It's called in mechanics conservative. What do we mean by conservative force? Conservative force means that if you have 2 points, A and B, it does not matter what path you reach from A to B, the potential between those 2 points will be the same. It depends only on the initial value and the final value. So it does not depend on the path that you take from A to B. And this is why the potential in the electrostatic potential will be just, if you have 2 points, will be what? VB minus VA. It does not have anything to do with how you go from A to B. Again, if you have 2 points and you want to get the gravitational potential, it is mgz2 minus mgz1. So it does not depend on how you go from, and this is because this force is what? Central. And because the force is central, you will notice that this force is what? Conservative. And this is a function of this is how the conservative field will work. So if we have a point here, and this point is point number 1, and I have a vector r0, and I want to calculate a function, for example, at 2, let's assume, and this is r, so this is just r equal to r minus r0, r minus r0, this is the amplitude, and this is the vector r minus r0. This is just the amplitude. So if we have the force, the amplitude of the force is just equal to c, some c over r square. So it's some c, and you have a force between 2 points here. Let's assume that those are 2 charges. Let's assume that they are 2 charges. So c will be divided by the distance between the 2 charges. In this case would be r minus r0 in between bracket here, and this will be square. So we can rewrite this if we want to write it as a vector instead of just the amplitude of the force. The amplitude of the force will be, the force in a vector form will be c divided by r minus r0 square. Then you need it in the direction of r minus r0, so this will be what? R minus r0 divided by the amplitude of r minus r0. Yes, guys, to get a unit vector in this direction, but this multiplied by this will give you what? The power of 3. So this is the force. So as a key observation, if we have a 1 over r, for example, let's assume that we have d by dx for 1 over r. So this is just d by dx multiplied by r. Here is just the distance, r minus r0. This is r, as I told you here, this amplitude here. Okay, guys? So don't be confused between this r and this r. So I call this distance r. If you want to call it r dash or r hat, or not hat, r1 or r2 or whatever. So 1 over r is just, with respect to x, is just 1 over r minus r0, the amplitude. And this is nothing more than 1 over x. And then what's the amplitude? It's x minus x0 plus y minus y0 square plus z minus z0 square. And there is 1 here. So if you do this and you differentiate, you will end up with x minus x0 divided by r cube. Just do it. This will be what? Square root. And you can bring it upstairs as the square root to the power of minus half. So you knew that if you have 1 over square root of x and you want to differentiate this with respect to x, this will be what? X to the power of what? 1/2. So this will be what? Negative 1/2 x to the power of what? 3 over 2. And then this will be what? Negative 1 over x to the power of 3 over 2 multiplied by 2 here. Yes, guys? But x to the power of 3 halves, let's assume that x to the power, this is just the amplitude, and this is the x squared to the power of what? 1 half, which is equal to what? X. So this will be equal to 1 over the square root of x squared, 2 over x squared, yes? So if you do this, you will notice that you will have this square plus this square plus this square, and you will have r, it represents r cubed, because it will be to the power of 3 over 2. To the power of 3 over 2 means the square root of this, it will be r cubed. And because you differentiate with respect only to x naught, x, in this case, this will be 0, the differentiation with this will be 0, the differentiation with this, and you will end up with x minus x naught here. So x minus x naught over r cubed, this is the first one. So if you try to differentiate with y, this is just as an observation. This will give you y minus y naught to the power of r cubed. If you try to differentiate with z for 1 over r, this will give you z minus z naught over r cubed. Why we are writing this? We are writing this to show you that those are the 3 components of what? Of what? Of the gradient. So the gradient of 1 over r is equal to what? X minus over r cubed in the I plus y minus y naught in the r cubed in the j plus z minus z naught over q in the direction of k. Of course, when you have any constants here, it does not make any difference. So 1 over r or c over r is a scalar potential field. Yes? Like the vector, like the potential field for what? Electrostatic potential is a scalar field. So the potential is what? Is a scalar field. So we are now taking the gradient of a scalar field. So if you take the divergence of this gradient of this field, you will notice that this would be equal to what? Laplace square of 1 over r, and this will give you 0. So divergence f equal to 0. Let's call this is f. So this is, let's now look at the divergence. So we define the gradient, and we said that the gradient is just a gradient of a scalar function. Again, I told you before that there is a gradient of a vector function, but this is called what? Tensor. Because this is a vector. If this is a vector also, you will have 9 components. Okay? So you will not have you will not have ijk. So you will have what? Then what? ij, ik, then you will have what? ji, jj, jk, and you'll have what? ki, kj, and you will have kk components. You will have 9 components for this one. If you will have 2 vectors like this, a, because this vector is what? ax. Let's assume that this is b. Like a vector like this. So this will be ax in the I plus ay in the j plus az in the k. And then there's no dot product or anything, just a vector like this. Bx in the I plus by in j plus bz in the k. Then you will have the multiplication of those three components, you'll have what? 9 components. So you will have AX, BX, II. Yes? Then you will have what? AY, BX, AX, BX. And then you will have AX, BY, IJ, AX, BZ, IK, and so on. Those are the components. So you can write this as a tensor in nine components. So the definition of divergence is just divergence of V is equal to d by dx for the component of V is Vx plus dV by dy Vy. Let's assume that the three components for the velocity field are u, v. This is the velocity field, and let's assume that they are u, v, and omega. Let's assume u, v, and omega. U, v, and omega. So this is du by dx, dv by dy, and d omega by dz. So this is a vector field, and this is the divergence of a vector field. So divergence always is what? So this is a dot product between two vectors. So this will give you a vector or a scalar. So this is what? A scalar quantity. And what is the application for this divergence? So let's assume that we have a fluid flow and we have a unit volume in cylindrical geometry. And here is our geometry like this. So this is x, y, and this is z. And let's assume that we have a unit volume of the fluid like this. So this is what? This is in direction of y, so this will be delta y here. This point here is just x and y and z. And this is in direction of x, so this will be delta what? X, and this is in direction of z, so this will be just delta z. So now, let's assume that I will look at this face here, where I have a fluid flow going in and out from this volume. So this is surface number 1, and this is surface number 2. So let's assume that we will have a velocity vector u as the component of what? U in the I direction plus v in the j direction plus omega in the k direction. If we have a velocity field like this, and u, v, and omega can be a function also of position x, y, and z. So maybe it's not uniform. So, and let's assume that rho of x, y, and z is just the density of the fluids in this field. So the mass flow rate into surface 1 will be what? The mass flow rate that gets into the surface 1. We knew that the mass flow rate is what? Density multiplied by velocity multiplied by what? By the surface area. So density is rho. And what's the velocity in this direction and in the y direction? Is v. So this will be what? V. And then multiplied by what? Multiplied by what? The area, which is dx dz. So this will be dx dz. But I am talking about the mass flow rate at this surface. So this surface is located at what? X, y, and what? Z. So what's the mass flow rate out from 2? The mass flow rate out from here. So it will be what? Can somebody tell me what's the mass flow rate? It will be
rho times v x plus dx.
Is it x plus?
Or x, y plus dy, and z.
So it will be rho v at what? We do not move in the x direction, or move in what direction? Y. So this y plus delta y. And z multiplied by what? Dx what? So what's the net flow? Will be just the difference between the outflow and the inflow. Yes, guys? So this will give me what? Rho multiplied by Vx y plus delta y and z multiplied minus rho v x and y and what? And z multiplied by what? Dx dz, which is equal to what? If we take the limit, if we divide here by delta y and multiply it here by delta y. So what's this? The volume. Yes? So, and if we take the limit for delta y goes to 0, this will give me what? Yes, guys? So if you will do this with what? With the x direction, and if you do this in the z direction, you will obtain what? Net flow in y direction. And net flow in x direction will be what? Similar to this. D by d what? X. What's the velocity in x? U multiplied by rho. And what's the net velocity in the z direction? Huh?
Omega. Well, net flow is d by dt.
But this is multiplied by the volume here. So this is multiplied by the volume. And this is multiplied by the volume. Net flow in z is equal to what? D by dz. Rho omega multiplied by what? dv. Okay, so, but the time rate of change of the total mass inside the volume, what's the total mass inside the volume? Density times what? Delta V is whatever the time rate of change of the mass inside the volume is equal to what? The net outward flow of the fluid. What's the net outward flow? So delta V goes with delta V goes with delta V goes with delta V, and you will notice that d rho by dt is just equal to the divergence of what? And this is what equation, this one? Yes, guys? So what does mean divergence here? So the divergence is just the net outward flow of what? In this case, what? Fluid mass, or the fluid. Net outward flow. So whenever you have any quantity, let's say, any quantity inside a volume, and you said that I have a divergence of xz u. This means that this is the net outflow of the quantity what? Of z. So to give some example, xz may be rho, which is mass, kilogram per meter cube or centimeter cube. So this will be the net outflow of what? Of mass. Yes, go ahead.
With your continuity equation, won't you need a rho?
Yes, rho here. Yes, yes, and there is a special case if your rho is incompressible. What does mean incompressible? Huh? Incompressible mean you cannot compress the fluid, so the density does not change. So if it is incompressible, so there is no change with density, so rho can get outside, and d rho by dt is equal to what? Rho does not change with time, it's incompressible. So it's equal to 0, so rho divergence V is equal to 0, or divergence G is equal to 0 for incompressible flow as a consequence of this one. So again, zeta may be the density, maybe, and if you study thermodynamics, maybe the specific heat at constant pressure multiplied by T. So in this case will be what? Will be joule per centimeter cube, and in this case will be the thermal energy, net thermal energy outflow from the volume, maybe is rho V, and in this case rho multiplied by V is just momentum per what? Momentum per centimeter cube, which is momentum density. So this will be what? The rate of momentum what? Outflow. Of course, momentum outflow will be what? Force. Yes, it's a force. Okay, guys. So this is some of the applications. So let's look at the curl for a field. And this will be the last topic of this chapter. Then we'll move to the next chapter, hopefully next Wednesday. So the curl of a field, sometimes they wrote it as curl of a vector A. So the curl is a vector quantity, but the divergence is a scalar quantity. So if we have curl of vector V is equal to the curl of vector what? V. And from chapter number 9, we knew that if you want to multiply cross product, so you get IJK in Cartesian coordinate, you get the components of the first vector, and the component of the second vector is Vx, Vy, Vz. What are the components of the del? D by dx, d by dy, and d by d what? By dz. Where V is just Vx, Vy, and Vz. Okay, guys? What does it mean? What does it mean if we want to look at application? So we knew from last time that the gradient of a field, a gradient of a scalar field, let's say potential or temperature or whatever, is the direction of maximum change of the field. This is what I told you last time when I said when you have this hump or a hill and you want to see what is the steepest direction of change or increase or decrease, it is in the direction of what? Of the gradient. Now we studied what? The divergence, and we showed that the divergence, the physical meaning of the divergence is what? Just the net outflow of whatever quantity of interest that you're taking the divergence of, let's say rho V or whatever. Now what about the curl? What does it mean curl? So let's assume that I have a rotating disk like this, and it rotates around an axis here with certain omega, and let's say omega in the z direction, so this is k. And I have a velocity, so the velocity will be tangential here. This is the velocity vector. So my velocity is just equal to omega cross r, and we knew this from a couple of lectures ago. So omega is the angular what? Angular velocity. And what is the direction of angular velocity usually? If it is vector, it will be omega in what direction? Here. If you want, this is rotating like this, so this is the direction of omega. And the direction of r in what direction? R in this direction. Yes? So whenever you will have omega cross r will give you a vector in what direction? In the theta direction. Yeah? if you are talking about cylindrical geometry. Okay, guys? So V is equal to omega cross R. So if we write this as the normal matrix IJK, for example, and in this case I will have omega does not have any component in X or Y, but has a component omega in what? In the K direction. And the R has 3 components, X, Y, and Z. The vector has 3 components, X, Y, and Z. So when you do this, you will notice that you will have negative omega Y in the direction of I plus omega X in the direction of J. This is just the vector V. If I want to calculate the curl of the vector V now, so all what I want to do is get curl of a vector V, and this would be equal to what? I j k, and I will have the components for the del operator d by dx, d by dy, d by dz, and the components of the vector V. Where is the components of the vector V? Negative omega y in what? In the x direction, negative omega what? Y. And in the y direction there is what? Omega x. And in the z direction there is no direction, because the velocity lies on the disk plane, and the disk plane is what plane? The xy plane. Yes, guys? So now when you will do this, you will notice that the results will be just, you will do this 0, and d by dz for a function of x is equal to what? 0, because it does not have any. And you will do the same, you will get 0. The only components is what? D by dx for omega x is equal to what? Omega. And d by dy for omega y is equal to what? Negative multiplied by negative is plus omega. So we will have how many omegas? 2 omega. So this is 2 omega in the k. What does it mean? It means that the curl of the vector is equal to what? 2 multiplied by the rotation vector. Yes? So if you have a curl, if you want to get a curl of a velocity field like this, it is just the rotation of this velocity field. So if you are in a fluid mechanics situation and you have normal flow, steady state, let's say laminar flow, you do not have any rotation. So the flow, here is a river bank, and the flow is moving uniformly like this. So there is no rotation. If you try to see, you will notice that this field does not have any rotation. But let's say in the middle of the river, you start to have a whirlpool, something like this. So in this case, the velocity will have a what? A curl. The velocity field will have a curl. Because now, if you are looking about this, and we are talking only about 2 dimensions, so this is x and y. And this is x and y. So the velocity is always in what direction? In y. But here it has what? X and y components. And you will notice that you will have what? You will have curl. What does mean curl? Mean that there is a rotation of your field. There is a rotation of your field. So if you have your curl of a vector quantity A is equal to 0, this means that the what? Vector field A does not rotate. You have a field that does not have any rotation. If you are talking about a curl that does not have a 0 value, this means that your field has a rotation on it. Like what? If you are washing your, let's say, your face on the sink, and then if the water goes gently, you will not see any whirlpool in the sink. Now increase the flow, what will happen? You will start seeing this. So when you will be able, let's say, by a computer simulation to visualize what's the component of the velocity field in the sink, and then try to get the curl for this velocity field, you will notice that the curl is not equal to 0. What does it mean? There is a rotation, there is a whirlpool going on. Did you understand? So this is the definition of what? definition of curl. And you will be able to figure out next time. I will just give a hint now, and I will conclude this chapter, hopefully. We are done by this, by the way, in this chapter. But if you have a curl of a vector field is equal to 0, I can represent the vector quantity or vector field as a gradient of a scalar function. A gradient of a scalar function. All of you, how many of you know the equation for Maxwell equation for electrodynamic? Anyway, the Maxwell equations are divergence of E equal to negative rho over epsilon naught, and curl of E equal to negative dB by dt. B is the magnetic field, rho is the charge, E is the electric field. So divergence of the magnetic field is equal to 0. This is called, those are the Maxwell equation. And curl of B is just equal to mu naught multiplied by J plus 1 over C squared dE by dt. What does this mean? This is called the Gauss equation. That the electric field is coming from what? From a charge. And this is it's called Gauss law. And this is called Faraday law. That the magnetic field, if you have a changing magnetic field with time, you will generate what? Electric field. And this is called magnetic monopole. What does this mean? The divergence, I told you, if you have a volume, and the divergence in the electrostatic is telling me that the divergence of E is equal to rho. So this means that the electric field coming out, divergence is the net flow. Yes? And the divergence of E is the net flow of the field line, electric field lines crossing a volume. And this divergence of E is telling me that is equal to something, is equal to rho. Yes? What's rho? Is the charge. So it tells me that the origin of the electric field that crosses the volume is coming from a charge. So what is the origin for the electric field? It's a charge. So what about the divergence of the magnetic field? It tells me that if this is a magnetic field instead of an electric field, it tells me that there is no single charge for a magnetic field to generate what? A net outflow of magnetic field. Why? Because if you have a magnetic field and you have what? North pole and south pole, they come together. There is no single pole. There is no single pole. So the north pole will do what? Will go what? Yes? What does it mean? It means that what's the net flow from the volume? Zero. So there is no single pole. So they call it monopole. And there is no monopole. Okay? This is the Faraday law. There is no monopole. This is called Ampere law. So in electrostatic, if you have no changing magnetic field, so this is called electrostatic. So curl of E is equal to what? 0. So we can write E as the gradient of a potential. The electric field is just the gradient of a potential, and then I can take this equation, substitute here. This will give you divergence of negative grad V is equal to rho over epsilon naught, and this will give me what? Nabla square V equal to negative rho over epsilon naught. This is Poisson equation for electrostatic. Okay, guys. So this is just I will stop here and continue next time. But this is just to tell you that if you have a curl of a vector equal to 0, this means that this vector can be represented as what? As a gradient of a scalar function. I will continue this next time.